As they say on the TV series, the story so far is I started out wondering whether there was a way to match tubes in tube amplifiers. And I use this as a kind of example or a prop, if you will. And so far we've looked at some triodes, and we'll talk about that in a second. In this segment, I'm going to primarily talk about these pentodes, and as many of you probably know, there's a variation of the pentode called a beam power tube that we'll talk about also and see whether the same technique is useful there. But before we talk about that, I thought it might be useful to review a little bit of what we've done so far. I drew this as a kind of simplified diagram of what happens when you're using an emission tube tester, and basically the grid is used as a plate and converts the tube into a diode, and then the meter simply reads the average current through that diode. I thought it might be better, in looking over the first two videos, I realized that I may not have been as clear about what I'm doing as I could be, and so I'm going to try to clear that up a little bit here. This is a simplified diagram of the tester that I'm using. Now, the tester I'm using has an auto transformer. The transformer is essentially connected across the AC line, and there's two different settings for whether high line voltage or low. We won't get into that for right now. And then the meter that detects how much current is flowing, you can select either the special or quality position. Now, there's a third position called leakage that actually works a little differently, but we won't get into that. That's mainly looking for shorts in the tube elements. But the AC line is brought through a resistor to the special position, and then a lower voltage, in other words, a tap off the transformer through a different resistor, is used for the quality position. And I'll talk about that in a minute, because whether you use special or quality depends on how much average current flows through the tube you're using. At any rate, the load control is just a resistor across the meter. So when the load control is set to 0, essentially the meter is out of the circuit. And as you turn the load control up toward 100, the meter becomes essentially more and more sensitive. The next thing is, so what have I actually been doing? Well, in the triodes, what I've been doing is, instead of using the grid as the plate, I've actually been connecting the plate to the P connection. In other words, I use the P switch for whatever pin is connected to the plate. I am grounding the grid. In other words, I'm connecting it to the K position. The cathode is also connected to the K position, and that's what K stands for, is cathode. The filament, in other words, there's a selector switch that selects a filament voltage, and that F connection is used to connect to one end of the filament, and then the other end of the filament is connected to K. Now, I'll just point out, in the case of a tapped filament, you need to make sure that that tapped filament is set to neutral. Otherwise, if it's left in the K position, then the full filament voltage will just be applied across half the filament, and you risk burning out the filament. But I hope that's clear enough to people who understand what I'm talking about. If not, you should read the instructions for your tube tester, but make sure that you have all of the positions that are indicated as neutral properly set on the tube you're operating before you try any of this. What I'm going to be doing today is hooking up pentodes in a variety of different pentodes. Now, some pentodes are used for power and others are used just for voltage amplification. We'll be looking at both kinds there. So one way to, this is sort of an overview of where we are. So far we looked at the idea of most people use mutual conductance tube testers. In an earlier video, I looked at the possibility of converting a tester into a curve tracer, and then I abandoned that idea, and I instead went to the question of, can we, in a tester which allows us to switch the pins around, can we switch the pins around so that we can use an emission tester to balance tubes? And if so, is that balancing as good as, better than, or worse than just using a mutual conductance tester? And for this purpose, I'm going to tell you a bad joke. I'm sure you've heard it. Two guys in the woods. It could have been two ladies, but at any rate, two people in the woods being chased by a bear. One of them turns to the other and says, "There's no hope. Bears can outrun all human beings." And the other one says, "I don't have to outrun the bear. I just have to outrun you." Well, that's what we're doing here. I'm not contending that using an emission tester in the way that I'm using it is better than a mutual conductance measurement or a curve tracer. What I'm saying is, for the explicit purpose of outrunning this one bear, that is matching two tubes or matching two sections of one tube, the results we get here have so far with the triodes been equivalent to mutual conductance. Once again, suppose you have three tubes. What you want to know is which two are the best matched, not how much gain am I going to get in my amplifier or any of those sorts of things. Now, in the first two videos, we did two kinds of triodes. We did 6SN7s and we did 12AT7s. We're now going to do pentodes. And in doing that, we're going to look at these. Now, we'll come back to this list in a minute. While I'm on the subject, though, I will mention that there are two related videos that I did some time ago, number 81 and 82. First is about how tubes work, and finally is about tube circuits. Now, if you are interested in learning more about tubes, and one thing about this exercise that has been useful to me is it has given me a lot of opportunity to both review and learn. This is one of the books that is available online. This is the hard copy, Electronic and Radio Engineering by Frederick Terman. Very good book. It was published originally as the Radio Engineering, and it talks a lot about tubes. Another one is Carl Spangenberg's Fundamentals of Electron Devices. I think this is available online. I'm pretty sure it is. Finally, of the books that, not finally, but almost finally, the Jacob Millman's Vacuum Tube and Semiconductor Electronics. These are in the McGraw-Hill series of electrical engineering texts. So if you're really interested in details about all of the tubes that we've been talking about, those might be some good references. I'll also mention the Radiotron Designer's Handbook, which I've mentioned previously. That's also a very good reference from the period. To summarize what we did in the first two videos, I show you this combined chart. For the 6SN7, we compared four tubes. We compared section 1 and section 2 of each tube using the B&K 707, the B&K 650. These are mutual conductance testers. And finally, a reconfigured TE50, configured as we showed in this diagram here. In other words, this configuration with the grid grounded and using the plate. We also did a series of 12AT7s, and once again, the 5 tubes we did there, these are dual triodes, so we did section 1 and section 2 of A through E. Once again, using the 707, the 650, and the TE50 reconfigured. What we concluded from this, or what I concluded from this is that in terms of just matching tubes, in other words, just beating the other person, not beating the bear, we're in the same ballpark using the readings we got from the TE50 as we would be from using the readings from the 707 or the 650. Now, you might get a better match if you used a laboratory quality mutual conductance tester. And I don't have any of those at the present time. They're very expensive. Usually they run well over $1,000 today. In fact, quite a bit over $1,000 if they're fully calibrated and tested and guaranteed. And so I can't tell you for sure that you wouldn't get better readings on a laboratory quality tester, but these are testers that were available in the day, and most of the people that use testers today use this kind of tester. It's known as the Hickok circuit, and it's also used in the Hickok models and most of the triplet models and all the others. So I hope that I have in the first two videos convinced you that at least when you're matching triodes, that you can do it with a reconfigured emission tester if the tester has the ability to switch the individual pins of the tube so that you can hook the plate where you want, the cathode where you want, the grid where you want, and so on. So what we're going to do now is we're going to try using this configuration to test some pentodes and some beam power tubes. We're going to be connecting the plate to the plate. We're going to be connecting the screen grid to the plate, that is this grid. We're going to be connecting the suppressor grid to the cathode. We're going to be grounding the control grid. We're going to be grounding the cathode. And then, of course, we're going to be supplying the appropriate filament voltage between the two sides of the filament. So let's see what kind of results we get. The first tube we'll look at is a 6V6. This is a beam power tube, and I chose this one to go first because in the amplifier schematic I showed you earlier, this is the tube type that's used in the output. In other words, there are a pair of these. Because I have a shortage of 6V6s at the present, my normal stock is currently in use in some tube amplifiers, so I'm not going to pull those out, and besides, those have been used for a while, so there may be quite a bit of variation in those. I only have one new old stock 6V6. I'm going to test that, but what I'm going to actually be doing is using the type 6AQ5. I have a number of those in new old stock condition. Now, the reason I use the 6AQ5 is, as you'll notice, for the 6V6, RCA recommends that you use the 6AQ5 for heater and cathode configuration considerations, application information, and characteristic curves. Now, and for this one, there is no characteristic curve shown. So let's take a look at the 6AQ5. So here is the data from the RCA tube manual for the 6AQ5. We'll talk more about the pin configuration a little later, but the important thing is that it contains both the pentode characteristics, in other words, when it's hooked as a pentode, in other words, a fixed voltage on the screen grid, and when it is connected in the triode configuration, that is where the screen grid is connected to the plate, which is the configuration we're going to be using. Now notice that these characteristic curves are quite different from these curves. However, what I'm going to assume is that if you have two tubes that match up in the triode configuration, they will also be the same matchup in the pentode or pentode configuration or pentode connection. Now, when I say I'm going to assume that, the reason I'm going to assume that is that many amplifiers in the first place use these pentodes in or beam power tubes in the triode configuration anyway. But even if your amplifier works in the pentode configuration, I think you're going to find that if you have two tubes that are matched as triodes, they will be similarly matched as pentodes. And remember, once again, like I say, we're only looking for relative matching. We're not looking for absolute laboratory measurement. So here is a new old stock 6V6, configured the way the tube tester was intended to be used. In other words, with the switches and everything set according to the tube chart. Pin 2 is set to the filament, and we'll be leaving that there. Pin 5 is used as the plate, and we're using the quality position of this switch and 30 on the load. And you'll notice that we get a reading here which I will say is about 74 on the meter. And so the next question is, can we test this tube in the Pentode configuration? To do that, remember, we need to connect the plate and the screen grid, that is pins 3 and 4, to the P position. We need to ground the grid. So we need to switch 5 back down to K, 3 and 4 up to P. So let's do that. And you'll notice that we get a very low meter reading. Now let's see what we get if we make the meter as sensitive as it can be. Turn it all the way to 100, and you see we get a pretty low reading. I would prefer, for matching purposes, to have the meter as high up as possible, because that way the percentage error is less. And as a result, in the quality position, I can't get the meter up into this area. So let's try the special position. But before we do, we'll turn the load all the way down, power off, go to special, power back on, let it warm up a little bit, and then we'll slowly raise the load control. Now you see, we can set it pretty much anywhere we want. What I'm going to do is set it right at 90. And you may say, well, that's pretty arbitrary. Yeah, because remember what we're trying to do. We're just trying to match tubes. So I'm going to set that right on 90, and I'm going to note that where the load control is, and I'm going to leave it there for all of the remaining tests. So I'm going to write down 90 for the 6V6. I have reset the load control, and I'll show you in a second why I did that. I'm now in the middle of testing the 12AQ5s, for which I have 5. I've already tested the 6AQ5. The setup is exactly the same except for the filament voltage. But let me now show why I had to reset the load control. We'll turn this on, and as it warms up, you'll notice the meter is reading, and in this case I read this eventually when it finally is warmed up, as 98. The reason I had to set the load control is when I started testing the 12AQ5s, which are pretty good new old stock tubes, every one of them at the old setting, that is the setting I started with on the 6V6, was off scale. In other words, past 100. So what I did was I found a setting that would keep all of the tubes in this range. Then I went back and redid the 6V6 and the 6AQ5 at that new setting, and the numbers I got were 83 and 68. And now this is tube A of the 12AQ5s, and I'm calling it 98. So now I'm going to go through and do the rest of the 12AQ5s, and then we'll go test them all on the 707 and the 650. I've commandeered the breakfast table for these tests with using the 707 and the 650. And back there are the, on the left is the 6AQ5 and then the 12AQ5s. You may notice the first 3 are Westinghouse and the last 2 are called standard brands. We'll talk about that more when we look at the results. I'm just writing them down here. And by the way, one of the reasons that I did the TE50 first is I wanted to be as blind as possible when I was doing these readings, so I wouldn't be influenced by how the 707 or the 650, which I have a lot more confidence in. Back there, by the way, are the 6SN7s and a couple of 12SN7s that I wound up testing for the original 2 videos. I didn't show all of these, but it gives you an idea of the range of these. You see, I wound up with 7 Sylvanias, 5 Zeniths, an RCA, a Raytheon, 2 GEs, and then a couple of Tungsol 12SN7s. So I have pretty fair confidence that my testing of 6SN7s is pretty is representative of what you're likely to find in the market. Okay, so let's get on with testing these Pentodes on first the 707 and then the 650. Well, you may remember that this was the plan that I started out with for this video, and I had a couple of gotchas and a eureka moment, and I realized that there's a better way to do all of this. So I changed the plan. You may remember that my original plan was to do these Pentodes and beam power tubes, and the revised plan is this one. That is, after reviewing the triode matching I did in a previous video, to just do the 6V6, or actually the 6AQ5, and actually not even that, but the 12AQ5, which I'll talk about in a second, and then the 6K6 and the 6AU6. And the reason is, here's the, I'll go to the eureka moment first, and then I'll come back to the gotchas. These are the results that I wound up with. And you may notice that instead of just presenting the TE50 reconfigured and the B&K 707 and the 650 in their normal setups, I have 2 new columns I'll talk about in a minute, and that's the eureka moment. What I realized after I got done doing some of this is that if you normalize the testers, in other words, for example, if you set the TE50 load control, basically the sensitivity, so that you get roughly the same number that you get, say, on the B&K 707, or you set the 707 to the same number you got on the TE50 for one tube, and then leave it there, you get remarkably consistent results, which I'll look at in a second. The gotchas were, that was the eureka moment. The gotchas are that while doing this, I discovered a number of things. One is I had some dirty contacts in my B&K 707. I had some dirty sockets in my B&K 650. So I spent a fair amount of time with the Oxit and other things cleaning these up. Now, I first worked on the 650, a couple of years ago, I think, at least, well, more than a year ago. And I cleaned all of the contacts at that time, but they had some had reoxidized, and some of the tube sockets needed to have some work. Anyway, several little gotchas that eventually I began to get very consistent results. So let me show you what those are and why the eureka moment, I think, contains some useful information for us. Take a look first at the 12AQ5s. I had 5 of those. These were the initial readings I got on the TE50 reconfigured as I showed earlier. That is, tying the screen grid to the plate, using the plate instead of the control grid for the emission flow, and then using the special position instead of the quality position to increase the plate voltage on the tube. Well, when I set the TE50 and the 707 to the same basic number on the meter, I began to get very consistent results. Notice a 94 here, 93, a 91 versus a 90. this one was a little bit further off. This one read a 91 on the TE50, the same as the one above, whereas this one only read an 88. But once again, 86 here, 86. So I moved on. Let's zoom out just a little bit here. I moved on to, one more thing on the far right. I also discovered that when I set the 650 to read 50 times the number on the 707, I started getting, and then divided the resulting numbers by 50. In other words, I normalized these numbers to be consistent with the 707, the same numbers on the 707 meter. Here's what I got. A 98 there, essentially the same as the TE50. A 94, a little different, but the same as the TE50. An 89, very close. Now there is a substantial difference, well, a noticeable difference, 91 versus 89, not big deal. 88 on the 707, 88 on the 650, once I divided the micromos by 50, and 88, 88. So what I discovered is that the 650 and the 707 are really doing exactly the same thing. The markings on the meters are just different. Once you account for the markings on the meters, they read the same. Furthermore, the TE50, once you normalize the meter readings so that the TE50 and the 707 read the same on this tube, they read the same on this tube and this one and this one and this one. Understand, once I set it up, I didn't change it. And I started getting very consistent numbers. So then I moved on to some 6K6s. And once again, I had 5 of those. Notice that here there is a little bit bigger difference. Notice that the 95 versus the 97 and 98, and the reason that is true is this bottom tube is the one I used to normalize. In other words, I set the 85 here, and then I set the 707 to read 85 using its sensitivity control. And so I got 85, 85, 85. Whereas this first tube is 95, 97, 98, 94, 94, 96. I'll let you kind of read that if you want to pause the video and look at the numbers. You'll see that, for example, this 80 came out to a 75 on the 707 and a 72 on the 650. A bit below this, but otherwise the numbers are remarkably the same. Finally, I decided to do some 6AU6s, and this is one of the places where there was a gotcha on the 650. The pin, the socket for my 6AU6 was very dirty, and I kept getting very inconsistent readings. I finally figured out what was going wrong. The TE50 was consistent, but the 650 was very all over the place, and it was just bad pin contacts. So I fixed those. I also had previously discovered that something in the 707 was causing a problem, and it turns out it was the switch, the lever switch that switches, the test 1, test 2, or test 1 switch that you'd have to depress on the 707 was dirty. So I had to clean it. Once I did, this 6AU6 read 51 on this, 52 and 54. 65, 66, and 63, 67, 71, 74. In other words, a bit higher there on the 6AU6. But what I think this shows is that when you are working with an emission tester like this, where you can switch the pins around, and you can have a position where you can use a higher plate voltage than the normal 40 or 50 volts that are used in these emission testers. And the nice thing about this particular tester is it has that. It's called the special position. So in the special position, with the pins configured to use the tube as it would normally be configured, and in the case of a Pentode, being connected like a triode, in other words, the screen grid connected to the plate, and I'll remind you of this schematic. We were connecting this screen grid to the P position. we connected the control grid to ground, or cathode. We connected the cathode to ground, or K, and then we set up the appropriate filament voltage. And what we got were remarkably consistent readings. In other words, my conclusion is that this tester, when set up in the somewhat unorthodox way that I have been using it, certainly not the way it's set up in the book that comes with the tester, but you get remarkably consistent results if what you're trying to do is match tubes. Now, as I've said before, I'm not claiming that this will substitute for a mutual conductance tester in all cases, nor am I saying that it will compete with a lab quality tube tester or curve tracer. But if what you have is a good quality mutual conductance tube tester, and you compare that to using this emission tester in the way that I've been using it in these last 3 videos, my conclusion is you come out with basically the same matching results. In other words, when you're trying to match a pair of tubes or to find 2 tubes that are very close to each other, the emission tester, properly reconfigured with the proper plate voltage, does just as good a job. So I invite people to try this themselves. Let me know, and others, what your results are. But for now, I'd like to say I hope you enjoyed this video. I certainly enjoyed making it, and have a nice day.